Okay, let's start. Good morning, and the first thing I would like to say is to thank the organizers, especially Professor Kamiyama and Miaopin, for giving me this opportunity to participate in this nice workshop. And today I will talk about neutron scattering, magnetic neutron scattering. This is a very general talk that I will use to introduce the concepts that later the other teachers will employ in the talk. Okay. How I can pass the slides? Not possible. This is the outline of the presentation. I will give some concepts about the scattering theory. I will orientate things to do a kind of rapid derivation of nuclear and magnetic scattering in order to understand why we can subtract in one diffractogram one part from the other. Then I will talk about the propagation vector. This maybe is the most important part for the other people that will continue in the school. Then the magnetic scattering derivated here for a general case will be adapted to crystals. And then I will introduce the concept of magnetic interaction vector and magnetic structure factor. And I will put some example on the problem of the phases in magnetic structures, and I will finish with some examples. Okay. Then let's go. The first thing is to introduce the different interactions between neutrons, X-ray and electrons with matter. This is taken from Roger Pine from a long time ago. Then the neutron see the matter via the nuclear strong interaction. This is an interaction that is very short range and very intense. Also, neutron is able, because a neutron has one spin, to interact via dipole-dipole electromagnetic interaction with the electrons, unpaired electrons in the matter. However, X-rays only see the electronic clouds around the atoms via the electromagnetic interactions, and electrons the same. Via the electromagnetic interactions, they are coupled with electronic clouds. You can see here also that electrons and X-rays penetrate not too much in the matter. However, neutrons penetrate too much. In fact, from the point of view of the neutrons, we can say that the matter is empty because the main interaction, the nuclear one, is with the nuclei. And nuclei are 10 times thousands smaller than the atom. And this is the reason for which we can model the nuclear strong interaction by the Fermi pseudopotential, as we will see in a few slides. I would like to introduce the concept of the scattering vector. Here is our incoming neutron. It's a particle with a wavelength, and this is the outgoing neutron, and this is the scatterer system. Okay? Then the difference between the incoming momentum, initial momentum, and the final momentum is the scattering vector. And then at the end of the day, all the experiments will consist to study how one neutron beam is being scattered by our sample, and then we need to measure how many neutrons and which energy are in every direction of the space after the scattering process. Here is this is the flux. I don't know why this is, okay, this is okay, the concept of a double partial differential cross-section. This is what we are measuring in our experiment. We need to count how many neutrons are scattered per second in a solid angle, defined in this KF direction, with the final energy EF plus delta, and divided by the energy. And this is the experiment. What we are doing every time is we send the neutrons, or we can say the same, neutrons, X-ray, or another proof to our sample, because this is a very general concept. And we need to count how many particles are scattered in a given direction. and which are given energy. And this is called double partial differential cross-section. We will see here that the main part of this is to calculate, this is the experiment, and we need to model how is the system that produces this double partial differential cross-section. If we integrate in energies, we pass to the differential cross-section. That means this is what one diffractogram is measuring, because we don't analyze usually in the diffractogram, in the diffractometers, we don't analyze in energy. We count for all the energies. That means that this is the quantity that we measure in a diffractometer. How many neutrons are scattered in a given direction? Doesn't matter the energy, because we are integrating for all the energies. And here we divide by the flux every time, because it depends on the number of incoming neutrons. And if we integrate for all the energies, we arrive to the total cross-section. Number of neutrons scattered per second divided by the flux. Okay, these are concepts that we will use in the next slides. Also, I need to introduce the Fermi pseudopotential, which is employed for the nuclear scattering of the neutron with the nuclei. And then the idea, because is the interaction is the nuclear strong interaction, that means that it's very short range and is very intense, and also because we are employing thermal or cold or not high energy neutrons. That means that this wavelength is much larger than the range of the interaction. Then we can use this Fermi pseudopotential. The idea is that we send one neutron that we model with a planar wave with an incoming momentum, and this planar wave is scattered by this point potential, punctual potential, with a spherical wave like this one, where b is the scattering length. It's a complex number, and far from the scattering potential, we have one detector, and then we can approach the outcome in the final wave with a planar wave again. And then here we have the scattering vector, and the spherical wave is here, and the Fermi pseudopotential, we adopt this form. It's a delta. And this is the scattering length. The B parameter, a complex number, tell us the phase of the outcoming wave, and also tell us how one scattered center is able to scatter one neutron. Not all the nuclei scatter in the same manner. Okay. This is an approach that is employed for this kind of neutrons with not too much energy. If the neutron's energy is higher, then we cannot use this. Then, don't worry about this, all these slides, but all these numbers. But by using the golden rules of Fermi, the conservation of the energy, and the number of final states for the neutrons and the flux, we can arrive to this double partial differential cross-section. That means the number of neutrons scattered in a given direction with a given energy, for a given, this is important, as we will see tomorrow, a given final polarization is this amount, this quantity. This is the conservation of the energy, and here we have Kf sigma f, the initial state of our neutron. Phi f is the final state of our scattered center. H int is the interaction Hamiltonian, and the initial, this is final, and initial states for the neutron and for the system. Modulus to the square. This is the key equation that we need to solve. Of course, this is the conservation of the energy, take into account the final energy of the system, initial energy, and the energy of the neutron. And then this is this part that appears here, this matrix element. You can put the Q is taking into account the coordinates of the neutron here. Sorry, the momentum of the incoming and outgoing neutron as here, and the Hamiltonian interaction of this element of matrix element take into account the polarization and the final states of the scatterer. Then the Hamiltonian will have one part which is depend on the nuclei and electrons, etc. One part which depend on the momentum of the neutron and the interaction, nuclear interaction, neutron matter and magnetic interaction, neutron matter. Here I define the amplitude operator. Amplitude operator is this matrix, this integral here. Is the integral of this Hamiltonian. This is nothing but scattering theory. Then we need to focus on the shape of this part and the shape of this. But I use this formalism because with the amplitude operator, tomorrow, as you will see, it's very easy to deduce the Blume-Malayev equations. Okay, then again, the interaction operator depends on many degrees of freedom, on the number of particles, on number of protons, number of neutrons inside the nuclei, and the coordinates of the neutron. Then, this was scattering theory. Now I will adapt for neutrons. For neutrons, we have the nuclear interaction operator. Now we are talking about operators. Then you need to take into account that in quantum mechanics, the operators, the rules of commutation is not trivial. AB is not the same that BA. It depends on the commutation rules with operators. Then the nuclear interaction operator is B that has, let's say, two terms. One is related with the scattering length, and another one is related with the spin of the nuclei. And this term, today we will not consider. We will focus only on the part related with the strong nuclear interaction, modeled by the Fermi pseudopotential, which is the scattering length, is with the one that appears here. Then with this operator, the interaction, the nuclear interaction operator becomes like this. That means that in the points where we have a nucleus, the neutron will be scattered by B, but B today is only the scattering length. And then this becomes a kind of summa of Fermi pseudopotentials. With this interaction operator, we can go to the amplitude, nuclear scattering amplitude operator, that we need to sum for all the atoms in the scattered system. And then it appears, you can put here, and it appears here again, the scattering vector. By using this expression and taking only the elastic part, that means that we will impose the conservation of the energy in the equations. We arrive to the coherent and incoherent nuclear elastic terms. The coherent one is here. It depends on the summa of pairs of particles, and at the end, this part will give you the correlation function between pairs of degree of freedom, in this case, between the positions. The incoherent part is only the sum to one particle, and will give you how the particles are moving in the system. Then here again we have the scattering length. With this, this is the coherent and the incoherent part. If we apply this part for crystals, that means that we have periodical arrangements of atoms. We have one unit cell that repeats periodically in the space. This will allow us to simplify this part like this. And immediately, by using the Laplace equation expression for the summa of exponentials, we will end up with this delta of the scattering vector for which we will have scattering neutrons is not any one. It must be one that is corresponding with a node in the reciprocal space. That this is the condition that tells us where we can expect diffracted neutrons. And the intensity of these diffracted lines is proportional to the modulus of the square of the nuclear structure factor. And this nuclear structure factor is telling us the intensity. And it's a kind of average in the unit cell. Now I'm taking only the unit cell of the content of the unit cell, how many atoms and which species of atom we have in the unit cell. Then we will use a different scattering length times the Boyle factor times this phase, which depends on the position of each atom in the unit cell. This is usually a complex number that for centrosymmetric structure, this becomes a real number. And we have here the Bay-Waller that is taking into account that the atoms are moving a little bit respect the equilibrium position. Then, this is what you are measuring in an experiment in which we will not have a magnetic scattering for the moment. Let's go to see what happened when we introduce the magnetic scattering. Imagine that it is a neutron that arriving to one ordered crystal, and then this neutron will create in every electron one magnetic field due to the spin of the neutron. That is, the spin of the neutron will produce a magnetic moment to the neutron, and this magnetic moment will create here a magnetic field. And then the Hamiltonian, the interaction Hamiltonian will be the dipole-dipole interaction between this, the magnetic field created in this point, with the spin and the orbit of the electron. Then, to do the calculations, the first is to consider the potential, the vector potential created by this neutron at this point. We can do vice versa. We can think that the electrons are creating here a magnetic field, and we can do the equations here, but it's the same, it's equivalent, vice versa. Then this is the potential that the neutron will create here. With this potential, which depends on the magnetic moment of the neutron, we can calculate the magnetic field at this point, and this magnetic field will be coupled with the spin and the orbit of the electrons here. And also, we need to change for the electrons, the momentum of the electrons, we need to change by electrical charge times the potential. By doing this kind of calculations and considering only less than quadratic terms in the potential, A, we can end up with this interaction Hamiltonian for the magnetic scattering, which is the magnetic moment of the neutron times something that depends on the orbit and something that depends on the spin. And this is an operator. The problem is to calculate the matrix elements of this operator. With this, if you put the previous, this one here, if you put this here in the amplitude operator that is coming from the scattering theory, you will end up with this shape for the amplitude operator. Sigma is the matrix, the Pauli matrix, and M, this vectorial operator is called the magnetic interaction vector operator. For the moment, it's an operator because I didn't take the matrix elements. And it has this shape. You can identify one shape, one part that is coming from the spin and one part that is coming from the orbit. And if you want, we can see that this operator is the perpendicular part of another operator to the scattering vector. And this another operator is the magnetic structure factor vector operator. Later, when we will go for crystals, we will pass from operator to vectors because we will take average values. And also we will use the dipolar approximation. But here, this is, you can see this magnetic structure factor operator produce this magnetic interaction vector, and with this magnetic interaction vector put in here, I have the amplitude operator for the magnetic scattering. Important is that if I add here something that is parallel to the scattering vector, I will end up every time with the same magnetic interaction operator. I have some kind of, it's not a bijective association. Then, we need to calculate the matrix elements, and this is not easy. We need to use Clebsch-Gordan, 9 and 6 symbols. And at the end, we can approach this magnetic structure vector operator by using dipolar approximation, like something that is proportional to the magnetization operator. We can do this. This step is not easy, but you can find many books. And this is what we call the magnetic form factor in dipolar approximation. That is something related with the Bessel functions and the G factor of the system. It's related, basically, this is related with the orbitals that have unpaired spins. Okay. And then you can see here also the previous lecture introduced the form factor of erbium. This is like this. And if you compare nuclear and magnetic scattering, in nuclear we have the equivalent to this form factor was the scattering length. And the scattering length didn't depend on the angle, on the scattering angle. However, for magnetic scattering, this form factor depends on the angle. You can see here that for high angles, the signal is going to 0. And in fact, this is like this because in nuclear scattering, we are talking about punctual interaction, and the Fourier transform of a point is something that is constant. However, for magnetic scattering, we are talking about electrons that are occupying one space around the atom. And then the Fourier transform is this form factor, basically. Then, the expression I put before, by using these ideas, can be rewritten like this. We have here the form factors, magnetic form factors, which are complex numbers, times the integral of one part that is related with the position and one part that is taking into account the correlations of the different components of the magnetic interaction operator at time 0, time t. This is the scattering when we can separate magnetic part from nuclear part. Sometimes it's not possible. Sometimes these two are connected. But if you, now I will do a kind of parenthesis, because this expression here is very general expression. For the moment, I didn't consider that the atoms are ordered in a crystal, but before to do this pass, this step, I will introduce the concept of propagation vector, which is very important in this school, propagation vector. And the idea is how we can describe the magnetic structures. We can use the magnetic moment in the unit cell. We can use different system of coordinates, Cartesian, polar, crystallographic, etc. And we will use the projections along the 3 crystallographic axes. But in crystallography, in the nuclear case, we use the repetition of a nuclear cell. We use the content of the unit cell and the repetition of this unit cell. And with magnetic structures, sometimes it's possible or sometimes it's not possible to define a magnetic unit cell. Remember that we are dealing with periodical magnetic systems. Then we can think the possibility to define a magnetic unit cell and the repetition, but sometimes it's impossible. And then we will introduce the concept of the propagation vector, which describes the relationship between the orientations of the magnetic moments in one unit cell and how these orientations propagate along the different nuclear cells. Let's see this with one example. Imagine that we have here one spin, one magnetic moment. Remember, magnetic moments are axial vectors. The transformation rules are not like polar, are different. That means that within prop operations, we need to add the determinant of the operation, which is negative. And then imagine one magnetic moment pointing along the B direction that in the next unit cell, if we are going, for example, along C, this magnetic moment is changing the direction, and so on. Then we can say that in the initial unit cell, the magnetic moment is, because it's pointing along 0, 1, 0, I will put 0, 1, 0, one phase. I use every time the crystallographic convention. Also in the scattering, I use this convention, 2 pi here every time. If you put 2 pi here, you don't need to put in the definition of the reciprocal space, and also in all the integrals, the 2 pi is not appearing because it's included there. And then if I put this vector 0, 0, 1 half times the vector that label the unit cell, I will reproduce this magnetic moment. For the other unit cell, magnetic moment in the unit cell one level upper along C is along 0, 0, 1 is 0, 1, 0 times this, and I put here the position of the unit cell, and so on. If I do like this, it's very easy to see that I can tell you the magnetic moment in any unit cell along, along this axis, 0, 0, L, is the moment in the initial unit cell times something that depends on one vector here, which is the propagation vector, and the position of the unit cell. You can put like this. Magnetic moment. I put here another index because sometimes, many times, we have different atoms, magnetic atoms, in the same unit cell. And then L is telling me the unit cell, and nu is telling me which atom in the unit cell. And it's one vector times this exponential. This is called the Fourier coefficient. Usually, this is a complex vector, and this is the propagation vector, and this is the position in the unit cell. And then here I introduce the concept of propagation vector. It's telling me in how many times the nuclear unit cell is included, if you want, in the magnetic unit cell. But what happens when this is not possible? For example, if we have incommensurate structures. Let me, before, to introduce commensurate and incommensurate. Commensurate is when all the components of the propagation vector are rational numbers. Rational numbers. That means that I can find one enough larger magnetic unit cell that includes the nuclear unit cell. And these are the most structures, ferro, antiferro, ferri, etc. And incommensurate when these are not rational numbers, but irrational numbers. And this classification describes the translational properties of the magnetic structure. But the result is the propagation vector. The magnetic structure will be the result of the propagation vector and the Fourier coefficients in each atom in the unit cell. Because we need to consider not only the propagation, but also the symmetry and how these Fourier coefficients are related in the unit cell. And these days, other lectures will explain about this. And then at the end, we have magnetic moment in a given position of a given atom, is summa for all the propagation vectors of the Fourier coefficients that are complex vectors. Again, if we have complex vectors and times this exponential, this phase. It's like if you consider that you have a periodical structure, you can do a kind of Fourier analysis, and these are the Fourier coefficients of your periodical structure, because at the end of the day, this is a periodical function, is you want. We can find many propagation vectors, but we can take the propagation vector inside the Brillouin zone, and with this is enough to describe everything. Then, let me analyze some case of the propagation vector. Let's suppose one propagation vector, and this expression here, let's use the exponential in this sinus minus I times cosinus minus I times sinus. Okay, I will use like this. Then what happens if the Fourier coefficient, this vector here, is real? And then if this is real, for example, I can. It happens when the propagation vector must be something like this one, 0, 0, 0, 1 half 0, 0, or something, let's say, trivial. Only in these cases, this Fourier coefficient can be identified with the magnetic moment of the atom nu, of the atom at the position nu. Then there is no change in the modulus of the Fourier coefficient, and there is only change the sign, the sign. And then remember, if this is real, magnetic moment must be a real vector, and then this part needs to be 0. And to be 0, the only cases is for given propagation vector like this one. And then I will, with this kind of Fourier coefficient, I will describe structures in which I have only change of sign from one lattice to the other. For example, ferro, K equal to 0, and this is real and constant. Antiferro for this kind of propagation vectors, or ferrite if you have more than one atom in the same unit cell. Let's go to see what happened again with the Fourier coefficient real, but not for propagation vectors that are not trivial. Then we need to include, for every propagation vector, we need to include the minus, because we need to ensure also that the Fourier coefficients, complex conjugate, are the same. At the end of the day, this quantity needs to be real. And then we need to impose conditions. Because this is real, this and this must be the same, are real, exactly the same. And then we need to sum for K and minus K. And at the end, I will end up with this expression. And this expression, if the Fourier coefficient here is real, is helping me to describe amplitude modulated structures. Collinear, but you can see that the modulus is changing. And this is, I can use this expression. General case, the Fourier coefficient is a complex vector. Then it's necessary to include the vectors and the complex conjugate for a given, for K is the Fourier coefficient for minus K. And then at the end, this must be real. You can say, okay, if this is a complex vector, the Fourier coefficient will have one real part plus one imaginary part. These both are vectors, and complex conjugate, I will change here the sign, because U and V are real vectors. And then magnetic moment will be described by 2 times this vector, cosinus this propagation, minus 2 times this vector, sinus this propagation. And this is what is describing helicoids, circular helices, when both modulus of the real and imaginary part are the same, and elliptical helices, if it is not the case, and when the propagation vector is not in the plane formed by these two real vectors. If the propagation vector is contained in the plane, this will describe cycloids. Then later I will go back again to the propagation, but now now we know how to describe the magnetic moment in a periodic lattice, and then we can describe magnetic crystals, and we can describe the nuclear interaction in magnetic crystals. If I take the expression, the last expression, and I take only the elastic part, that means that I can, the correlations, I can decouple the correlations between the different components. And if we have a crystal, this part here, and if we have a crystal, and if we decompose the magnetic moment for each atom like a summa of, by using the formalism of the propagation vectors, then this position of the lattices will appear here. Here you can see the form factor, you can see the scattering vector there, the coordinates of the atoms, and this is summed for all the atoms. But now, by imposing that we have a crystal, this kind of summa will become a kind of delta. And here already we use the dipolar approximation, and we have the components of the magnetic moments along one direction. Sorry, not the magnetic moment, the magnetic interaction vector, which is a complex vector, in one direction and in the other direction. Magnetic structure factor. Now this is a vector. It's not anymore an operator because we use the dipolar interaction. We take matrix elements, and then we have this magnetic structure factor, which is a complex vector, and is the magnetic moment of atom M times one phase, which depends on the position, times the Debye-Waller, times the magnetic form factor that I described before. And with this magnetic structure factor, this is coming from one with this magnetic, okay, yes. With this magnetic structure factor, we can define the magnetic interaction vector, which is the one that appears here, the magnetic interaction vector. Then, by doing this, for crystals, magnetic elastic scattering for periodic arrangement of magnetic moments, the magnetic contribution is something that remembers the nuclear one, but here in the delta we need to add the propagation vector. That means that we will have a scattering in the positions of the reciprocal, in the nodes of the reciprocal space, plus minus, I need to use plus minus k, the reciprocal, the propagation vector, sorry, times the modulus square of the vector, magnetic interaction vector, which is a complex vector. What is this? This vector that enters in the expression is the, let's say, the magnetic structure factor minus the projection of the magnetic structure factor along the scattering vector, which is the blue part. If I subtract the red one minus the blue one, I will have the part of the magnetic moment arrangements that are contributing in the intensity here. That means that only the perpendicular part of the magnetic moments to the scattering vector for every scattering vector will contribute to the scattering. The magnetic scattering is strongly anisotropic. Let's see with one example. Imagine that we have this arrangement of magnetic moments with one spaceman D, and then this is the neutron that arrives with a wavelength, and it's scattered, following the Bragg law. In this case, what do you think? Is scattering or not? They are not scattering because magnetic moments are parallel to the scattering vector. With these magnetic moments, I can calculate the magnetic structure factor will be parallel to this. And the component perpendicular to Q is 0, then not scattering. And which is the reason of this? Is because then this neutron, when we will enter in this material, we will not see any contrast in the magnetic field lines. If magnetic moments are ordered like this, these planes, the average magnetic moment in the planes is 0. The same happens for every plane in the crystal. Then this will not be scattered, and the equations tell us that will not be scattered. However, if the magnetic moments are like this, same neutron arrive, and in this case we will have a scattering, because in this case you can see that we have planes with a net magnetic moment different, for example, from this one, and then this neutron will see a periodic potential and will be scattered. This is the, let's say, if you want, the physical origin of these equations. Summarizing, I will go to this one. For nuclear scattering, we have this, when we can define nuclear structure factor. For magnetic scattering, every time nuclear elastic, magnetic elastic, coherent, we have the same delta, but we need to consider the propagation vector here. And also, if for nuclear scattering, we have a nuclear structure factor modulus square, which is a number, and for magnetic scattering, we have the magnetic interaction vector modulus square, which is a complex vector. This is a complex number, complex vector. And this is coming from the magnetic structure factor in dipolar approximation, because this is proportional to the magnetic moments. And we need to consider only a scatter in magnetic scattering. We will have a scattering in the reciprocal lattice nodes plus minus propagation vector. And at the end, this is the expression I would like to arrive. If we don't use polarizing neutrons, we have in one side nuclear scattering and in other side magnetic scattering, and both terms are not coupled. Tomorrow we will couple both of them. That means if I want to determine the magnetic structure, I need to extract this part, and I can measure one system in a paramagnetic phase, then this is 0. I can measure this, and by subtraction, I can, by measuring in the magnetic ordered phase, I can determine this part. Again, something more about propagation vector and Fourier coefficients. Now, this is a crystal. Imagine a ferromagnetic crystal with only one atom by unit cell, and then, in this case, propagation vector is 0. This is the Fourier coefficient that describes this magnetic moment, and is the same for every unit lattice, is the same for every atom, And then I will observe, in the same points where I can observe nuclear scattering, I can observe magnetic scattering, in the same points of the reciprocal space. If I have a propagation vector 1/2, for example, one antiferro along the A direction, and the magnetic moment pointing along B direction, then the Fourier coefficient will be like this. This is the propagation vector, and I will expect magnetic signals in these points in the reciprocal space. Is the nuclear unit plus minus 1/2, in one side and to the other. These are called satellites. We'll observe like this. If I have an antiferro, but now with 2 atoms by unit cell, I will have 2. If it is the same atom, 2 Fourier coefficients, and the Fourier coefficients will be related by this expression. One will be the opposite to the other, and with zero propagation vector. Many times people think that with every time we need one vector different from 0, 0, 0 when we have antiferro. But it's not the case. Cannot be the case if we have several atoms in the same unit cell, for example, here. And then, in this case, we will observe magnetic intensity in the same nodes of in the same positions that the nuclear one in the reciprocal unit, in the reciprocal space. Sometimes the space group don't produce for a given unit cell, don't produce nuclear scattering, but sometimes the magnetic scattering produce magnetic scattering intensity in these nodes, because the symmetry, the magnetic symmetry is reduced, but the lattice is the same. Imagine a candid antiferromagnet. Dimitri will also explain something about multica structures, and here a candid antiferro, we can see that is a kind of ferro indexed with this propagation vector, plus one component that is antiferro propagating in this case along the a-axis. For example, if I use the Fourier coefficient for the 0, 0, 0 propagation vector, a component along the b-axis and a component along the a-axis as the component that propagates with 1/2, 0, 0, then I will describe this magnetic structure with two different cases, two different propagation vectors. And we can expect increasing in the magnetic signal in the nuclear points in the reciprocal space, and we can expect also satellites. If we have amplitude modulated structures, for example, one propagation vector like this, Kx is something, and the Fourier coefficient 0, my0, that means something that is parallel to B, and with this propagation vector, I can represent this sinus modulated structure, and it will produce this kind of satellites. And also, if I want to, this is a cycloidal structure. How I can represent this with a propagation vector? The cycloid is propagating along A, then propagation vector is like this, and with this complex vector, which is this complex vector, U and B includes Kx. Then this is a cycloid, and I will expect satellites like this. And if it is a helicoidal structure, the same, but now Kx is not contained in U and B. Okay? And also I will expect satellites like this, because in this case it's propagating along A. If I put the propagation along B, the satellites will appear in the other direction. Okay? Solitonic structure, for example, what is happening many times in helicoids when you apply a magnetic field perpendicular to the conical helix, and then you need to use one propagation vector and the harmonics. And this is a zoom. It's a zoom. I have the nuclear Bragg line, and I can observe sometimes many harmonics to describe this kind of solitonic structures or square structures. Then I have still 10 minutes. I can tell you something about the problem, the phase problem in magnetic structures. What is happening many times is that different magnetic structures, the idea is that you are measuring the modulus of the magnetic structure factor. Then you are losing, this is a complex vector, but you are losing the information contained in the phase. At the end of the day, that means that you can have the same pattern, if you want, but for different magnetic structures. For example, I put here one magnetic structure in one dimension with 0, -1, 0, +1, and this magnetic structure is described with this expression when I consider the phi equal to 0. if you put phi equal to 0, the same phase for all the Fourier coefficients, for all the atoms here, you will describe this one. If you, however, put phi equal to 90 p over 4, you will end up with this other magnetic structure. In both cases, with neutrons, you will not be able to distinguish this because there is a constant phase that relates one and the other, constant phase that you apply for all the Fourier coefficients. And this is the propagation vector in this case. This is something that we published several years ago. In this case, in this cobaltite, calcium cobalt oxide, oxygen, these and these magnetic phases are indistinguishable by using neutron diffraction in powders. In both of them, the magnetic moment in the unit cell is 0, because this is 0 and this is equal to this one. And here, also the magnetic moment also is 0. But you can describe the magnetic structure with this propagation vector in this space group, and then you will end up with this modulus of the magnetic moments by changing the sign, of course, minus, etc. And you can use this other way to describe the same pattern by using this propagation vector in this other space group, and here you will end up with this other. And what is happening is that if you use the Fourier coefficients in one model and you add one phase, which is 2 pi over 12, that means pi over 6, to the Fourier coefficients that describe one or the other, you will end up, you can understand that both are not distinguishable by using powder diffraction. Of course, you can say that this is not possible because you cannot understand physically why the magnetic moment here is not ordered. And then, by using different physical arguments, you can go from one to the other. You can say, okay, this is the good one. Okay, now I have time to do some example, at least two examples. I would like to mention the first example measured long time ago, published in 1949 by Schul and Smart, and this is the magnetic structure of the manganese oxide. What they can do to determine this magnetic structure, they measure it, in fact, at room temperature, at 20 Kelvin, 20 degrees Celsius, and for manganese oxide, they measured two peaks that are related with the nuclear structure. And then these two peaks are explained by the unit cell of the manganese oxide plus the position of the manganese and oxygen in the unit cell. You can see the quality of the data correspond to the quality 70 years ago. Now it can be much better. When they cool down the sample, they enter in the ordered phase, 80 Kelvin, because the system ordered at 120 antiferromagnetically. Then at 80 Kelvin, the system is magnetically ordered. That means that the system has a nuclear periodicity plus a magnetic periodicity. And the magnetic periodicity will contribute to this magnetic backscattering here. Sorry, this one. This peak has magnetic origin, and also this one, and also this one. Then by subtracting or by analyzing together with the nuclear and magnetic part, they can determine easily that there is a propagation vector that is 1/2, 1/2, 1/2, and the magnetic structure for this compound is like this. Okay, this can be done, for example, at D1B or D20 or any other instrument, but because I was working in D1B, I prefer to use D1B. or if you want, this is with cryostat, with furnace, or you can do also a STEAMD or other instruments all around the world. But because also this is a new instrument at ILL, I would like to do publicity of this. Also here you can measure powder diffraction and single crystal diffraction. Let me finish with this example that I measured in J Park long time ago with Miaopin, was my local contact. And thanks to this experiment, we are here. And this is one system that ordered form a kind of helix of long period. You can see here 480 angstroms of period. It's chromium niobium disulfides, and is a monoaxial chiral magnet. It's monoaxial. There is a strong anisotropy on the planes, but from one plane to the other, the spins are turning. And you can see here, it forms a period helix like this. This system, when you apply a magnetic field perpendicular to the helical axis, it forms a solitonic structure like this one. If you apply a magnetic field parallel to the chiral axis, it forms a conical structure. Both cases are, the physics of one and the other are totally different. In this case, you will finish with a nucleation phase transition, and here with instability phase transitions. But when you are dealing with very long period helical structures, it means that the satellites will appear very close to the nuclear Bragg peaks, and sometimes you cannot differentiate. And imagine, this is with a normal resolution, the width of a Bragg line, and if you increase the resolution, sometimes you can observe very small satellites very close to the Bragg peak, nuclear Bragg peak. And then this is the cause. Many times these compounds has been described like ferromagnets, because it's very physically, one very large period helix is like a ferromagnetic domain that is moving slowly. Then you cannot differentiate. But we were interested to see if this was, if correctly something that has been described like ferromagnet is really or not one helix or not. Then the idea is to measure the satellites in two compounds that, the chromium niobium disulfide, of course, is not, we know that is a helix, but we measure the satellites. But in the chromium tantalum sulfide, the system was described like ferro, but we can demonstrate that it was not a ferro, it was a helix. And this was done at, at J Park, at Super HRPD, at MLF. You can see here in blue the nuclear structure 160 Kelvin, and in red, when you call down below the ordering, and you can see that appears satellites for a given peaks. But you can see here the resolution. Is thanks to this resolution, we can measure these satellites. The same happened for a chromium tantalum. We were able to measure the satellites. And this was, also you can go for suns to measure this, but in wide-angle diffraction. And we were able to measure this very small propagation vector, 0.02 or 0.05 reciprocal units. Okay, then I will stop here. Thank you, all of you, for your attention. I have more examples. Okay, this is important. I recommend the bibliography, I recommend the Squires and the Lopsy, and the two talks I will give you today and tomorrow are in this part, in this chapter that I already gave, is is in the material that I give to you. And thank you for your attention.
Thank you very much. So now his lecture is open to question and comment. Right? I think it's a very good chance.
Hello, sir. Good afternoon. Thank you so much for your lecture. You said that we define this propagation vector in order to refine magnetic structure.
To describe magnetic
structure. Like, for example, if you have an antiferromagnetic or ferromagnetic, they have a particular propagation vector. But if the system possesses both, like ferromagnetic as well as antiferromagnetic, so in that case, how do we define propagation vector? Do they change, or means what is the methodology for that?
I don't know if I understood correctly your question. We use the propagation vector formulas to describe the magnetic structures.
Yes.
Your magnetic structure at the end is a function that at every point in the unit cell is a vector function, is assigning one vector. Then, because this function is periodic or has some periodicity, you can do every time, if you want, you can do a Fourier transform and decompose in the harmonics. And the harmonics are labeled by the propagation vector. This is mathematical formalism. And the Fourier coefficients is how is the amplitude of each harmonic.
Okay.
And this is very general. You can every time describe your magnetization function by using this kind of harmonics.
Okay, okay. And we do this, like we give this input of a propagation vector before starting for the refinement.
More slowly, please.
Sorry. Actually, I don't have a habit of this. Means we define this propagation vector before going for the magnetic refinement, isn't it?
Also, the propagation vector, you can, these days you will see that also the propagation vector is related with the phase transitions, because is the wave vector of that in the phase transition. You will see something equivalent to describe the propagation vector.
Okay. Thank you so much.
Thank you very much. Other questions? Okay, we have plenty of time in the for 6 days, so maybe let's finish today. And let's thank the lecturer again. Thank you very much.